Find the average rate of change between 2005 and 2010. The table that we see below is showing us the average cost of gas between the years 2005 and 2012, and all of the values are given in dollars. When I want to find the average rate of change, it's the slope between 2 points. So I want to think about the change in my y values divided by the change in my x values, or the change in my input values divided by the output values over the change in my input values. In this particular table, the way that it's listed, our input is actually y. This would be what you normally would call x. And our output is c of y, and that's what you would usually call y. So again, this is our input, and this is our output. So I am going to take the output from 2010. Let's see, that is this value, 2.84, and subtract off the output from 2005, which is 2.31. And then I'm going to divide by the input values, 2010 minus 2005. 2010 minus 2005. The first two numbers are the ending point, and then the second two numbers are the starting point. So let's calculate this. I'm getting 0.53, and that's over 5. So it looks like over a 5-year period, the price of gas changed by 53 cents. And let's divide that. So we're getting 0.106. So this would be, this is listed in dollars, right? That's 10 cents, or rounding to 11 cents per year. For each year, it's about 11 cents if we round up. Most of the time when we're finding average rate of change, we don't have a table like that. We've got a function that we're trying to use. So our average rate of change is going to be calculated as f of our second point minus f of our first point over x2 minus x1. Again, x is our input and output values. So in this example, x1 is 1 and x sub 2 is 9. So what happens if I plug 1 into this function? What's the output value? I'm going to have 1 minus 2 times the square root of 1, which is 1 minus 2, or negative 1. And what happens if I plug 9 into this function? I get 9 minus 2 times the square root of 9, or 9 minus 2 times 3. 9 minus 6 is 3. Okay, so I need to know my output value so I can plug them into this expression here. So f of, this is f of 2, our second output value is 3. And then our first output value was negative 1. 3 minus negative 1 divided by, and then our input values were 9 minus 1. So it looks like our average rate of change here is going to be 3 plus 1, which is 4, over 10, or simplify that to 2 over 5. Let's do another example. Let's find the average rate of change for this function between -2 and 4. So our first value, x sub 1, is equal to -2, and x sub 2 is equal to 4. I want to plug both of those values into the function to get their output values. So f of -2 is 5 minus 2 times -2 squared. That is 5 minus 2 times 4. 5 minus 8 is a -3. Let's do the same thing for our second value. What's f of 4? So I'll have 5 minus 2 times 4 squared. 5 minus 2 times 16. 5 minus 32 is -27. Okay. So this is f of x1, and this is f of x2. So our average rate of change is f of x2 minus f of x1 over x sub 2 minus x sub 1. All right, that's a -27 minus -3 over 4 minus -2. So -27 plus 3 will give me -24. And then 4 plus 2 will give me 6. So it looks like my average rate of change is -4. For example 4, we have a graph of a function, and we want to use it to estimate the local extrema of the function. Again, the local extrema are where we have a local maximum and a local minimum. This function is growing endlessly on the right-hand side, and it's going down endlessly on the left-hand side. So it does not have an overall maximum or an overall minimum. So this has no what we call absolute maximum or minimum. That would be a maximum for the whole function, a minimum for the whole function. But we do see that we've got a local maximum here. We have a local max at -128. And we also have a local minimum point here at 5, -80. Now, I used Desmos to find these values, but as you move forward into calculus, you'll have different techniques to be able to find what those values are for the local max and local min. We know that something is a local maximum if it's changing from increasing, we can see the graph is going up here, increasing to decreasing. That'll be a local maximum. A local minimum will show up when we have a function that is going from decreasing to increasing, like we do here. So let's talk about where is the graph increasing and decreasing. Well, it looks like the only space where the graph is decreasing is on this interval here. So I'm going to say that the graph is decreasing between, and we use the x values to tell us where the function is increasing. So between -1 and +5. I should say decreasing on. The other parts of the graph is where the graph is increasing. So it looks like it's increasing here and it's increasing here. So the graph is increasing on. So for the left-hand side, I'm going from -infinity up to -1. Again, we're asking what the x values are. And then we're also going from 5 up to positive infinity. Now, notice that I have round parentheses at both the max and min points, right? At 5 and at -1. Those are not included because when we're right at those points, we think that the graph is technically has this little break of a horizontal, what we call a horizontal tangent, and right at that point, it would be like right at the top of a roller coaster. The graph is neither increasing nor decreasing, so we don't include those points right at the local max and the local min. Let's do one more example like that. Here's a different function, again, graphed in Desmos, and we can see that we've got 2 points that look like they're local minimums, and then we've got 1 point that's a local maximum. So we've got, oops, why are you not working? There we go. There we go. I've got a local minimum here at negative 3.15, negative 52.63, and I also have a local minimum here at 2.04, negative 37.04. And then we have a local maximum at negative 0.39, 0.98. Now this function is growing on both sides endlessly, so we don't have an absolute maximum. But do we have an absolute minimum? It looks like the graph doesn't go below this point right here. And so I think that this is not just a local minimum, I think this is actually an absolute minimum. There are no values that are lower than that. All right, let's talk about where the graph is increasing and decreasing. So it looks like our graph is decreasing on a couple different spaces. First, over here on the left, and then here in the middle. I think I've got those two areas of decreasing. So we think that our graph is decreasing on negative infinity to, what's the x value here? Negative 3.15. And then also, I'm going to draw it down here, from the x value here is negative 0.39 to 2.04. Again, we grab the x values because those are the values that lead to parts of the graph that are decreasing. All right, where's the graph increasing? Well, on all the other spaces. The graph is increasing here and here. So this graph is increasing on, let's see, negative 3.15 to negative 0.39, and then from 2.04 up to positive infinity.